let's go back though, because this was another question. Okay, accuracy. All right. Remember, I told you before that the gravity measurement itself is accurate to about 0.001 millivolts. So the gravimeter itself has that kind of accuracy. Some people say 0.01, some people say 0.001. It doesn't matter, because the fact is that we can never measure elevations, or very hard to measure elevations, particularly on ground, within 3 centimeters. We just don't have the ability to do that. Maybe we can get a foot or so, but 3 centimeters is a tough hole. So that's what I mean when I say that the limiting factor in a gravity value is the knowledge of the elevation. If I'm off by 3 centimeters there, my gravity value is off by 0.01 milligauss. Okay? And really, this is a relative measurement, right? So you might actually be able to get, it's not an absolute error. It's basically the elevation difference between points. So if you're on perfectly flat ground, or very, very minimally sloping, you might be able to get 3 centimeters of accuracy. If, on the other hand, you're on a topographically complex ground, mountains, or pretty much anywhere other than the Central Valley in California, you're going to have a hard time. And so understanding elevation is one of the keys. So if I'm in an area with complex topography, it's going to be hard to get really accurate gravity readings. All right? That's actually a really important truism. All right? Gravity works best in terms of accuracy where the ground is flat. The more complex the topography, the worse gravity gets. For two reasons. The first reason is obviously the accuracy of the elevation, right? How accurately we can measure this. What's the other reason? Well, it's actually a couple of reasons. First of all, when we're on complex topography, what's the geology like? Well, it's pretty complex. You don't have flat layers when you're on mountains, right? You might have dipping layers with strata, overturned folds, something like that. So the idea that a single density actually represents the correction that you need, and that an infinite slab represents that correction, are both erroneous, right? Just doesn't work that way. So, for both of those reasons, gravity accuracy is going to be worse in complex topography. So just keep that in the back of your mind. That's a great test question. Okay, let's move on. So this is an example, and I really don't want to go over this carefully. It's kind of old school. I mean, really old school. This is the way that was developed to do terrain corrections back in the day. And basically they subdivided, and this was the gravity measurement, they subdivided the area around the gravity measurement. So you can think of this as a map, okay? So let's imagine that we have a map of topography. So let's say that we've got a mountain here, maybe we've got a little valley here. So this is pointing this way, and this is pointing this way. make a measurement right here. This is a gravity measurement. Okay, so this is topography. Okay, so what happens here? Well, this mountain, if I assume a slab, let's take a cross section of this just for grid. So I'm going to take a cross section right between this. So I've got a mountain, and then I've got a smooth syncline like that. And I'm making my measurement kind of right in between. There's my measurement, right? So what do I have going on here in terms of the Bouguer anomaly? In terms of the Bouguer anomaly, if I compute an infinite slab, maybe an average infinite slab, all the way down to sea level, you can see that I've got more mass here than the infinite slab, and I've got less mass in here. So the Bouguer anomaly in this case is going to be wrong, and it's probably going to overcorrect the data, right? Because the slab is not all full of rock. So what we do after correcting for the Bouguer anomaly is we do terrain corrections. Right? So what we say is, oh, this position here has gravity pull. Let's say this position, actually, let's say that it's do this. This position has approximately the gravity pull of a point pulling up. Okay. This position right here doesn't have any gravity pull. Okay. Because it's air. And so I go along around the measurement position with a template and figure out what the gravity pull is in each of those little sectors. I add all that up, and that's what's called the terrain correction. It can be positive or negative, depending on what the topography is around the site. Now, what do you really want to do to that? Let's look at another example. And before we do that, what we need to do is look at what is the true pull of gravity from here to here. All right? And what we're going to assume is that this is not a square, but actually a circle, a sphere, if you will. So let's look at the arbitrary gravity action or gravity attraction. Can you, what do we do here to get to the next? What? Yeah, we want to go to the next one. Hey, we have a clock here too. Yeah, the next lecture. There you go. Okay, let's go down to. There's a lot of other information that obviously I can't get to. But let's look at this for the time. Okay, so this is the gravity anomaly of a buried sphere. And we're going to go back to this. Okay. Actually, we'll do this to look at the terrain correction to begin with. So, how do we simulate the gravity anomaly of any body? Well, what we do is we basically make a whole bunch of spheres in the subsurface. So we just populate this whole thing with spheres. Okay? And in the computer, we really think of them as squares, but we're just going to basically say they're so small that we can think of squares and spheres as the same. It turns out, and you can do the math on this, that the gravity anomaly due to each point mass is given by G, the difference between the mass in the body and the mass outside the body, multiplied by the depth of the point sphere, divided by h cubed, which h cubed is simply, now it's a terrible difference. H is the distance from the sphere to where I'm making the gravity measurement. So h is not h, in this case, as I discussed it earlier, okay? And that's one of the problems in geophysics is we throw variables all the time into the equation. You'll see this actually worse in electromagnetics. There are so many conventions for variables. You've really got to avoid, you can't look at a variable and say, okay, I know exactly what that variable is. Pi, yeah, you can do that with pi. You can probably do that with cap G, although I've probably screwed up a few times. What are some other ones that you can use? Epsilon is almost always a small number, but not necessarily. So there are very few variables that you can get. X, Y, and Z are usually spatial dimensions. T is usually time. But geophysics kind of just uses these variables in very arbitrary ways, unfortunately. Okay, so if I have a varied sphere, and let's just go back to that really quickly and look at, there's a bunch of discussion about what a gravity anomaly of a varied sphere is, but let's just look